Okay, so before we go into any further on how to write these linear and exponential equations, first let's look at just the basic building blocks of models. So in modeling, what we're doing is we're taking a real life something and we're trying to put it in a different format, which can help us see things better or how work with them better. So, for example, other fields use models. So, for example, like architects, they may make a scale model of what they're working on, so they can see it they can see it overall in a more manageable size. There's roadmaps, um, which help depict, the roads. They may not look exactly like what the roads look like, but they are um, it's a better way sometimes to see how the roads interact and where to get from one place to another. So when we're looking at mathematical models, we're doing something similar. We're going to take this real world situation and we're going to try to put it into a way that we can start working with it and we can answer questions regarding it. So mathematical models work best with relationships between quantities. And we're looking at something that can change. For example, a relationship between wind speed and stress on a bridge, or a relationship between work productivity and unemployment. Um, so we're going to take these mathematical models and we're going to create what we call functions. This is going to tell us that relationship between those two quantities that we're looking at, and models are built up on these functions. So some aspects of functions. The first thing we need to know is, so functions, they are using variables. So variables are those quantities that are changing. Um, and there are two types of variables. There's dependent and independent variables. Let's see a little better that way. So just like the words imply, dependent variables are dependent on other things, and independent variables are not. So for example, if we're comparing time of day and the temperature of the air, one of these is going to be dependent on the other. So the two things we're describing here, of course, are time, the time of the day, and the temperature. So which one is which? So does time depend on the temperature, or does temperature depend on the time? Well, obviously, temperature is going to be the dependent variable because the temperature of the day depends on the time of day, right? So it's going to be colder in the morning at night and warmer during the day because of the sun, right? Time is going to be independent because it's just the passing of time. And it's not, it doesn't depend on anything. It just depends on the rotation of the sun, right? It just happens. So most of the time, when we're talking about time, it is going to be the independent variable. The only time it might not be is if you're looking at like a duration of time. So like reading a book and how long it takes to read that book. That's like a duration of time and not necessarily just the passing of time with the sun going up and down. So a few different ways we can talk about independent, dependent. We can actually use the words depend. So temperature depends on time. We can also, instead of using the word depends, we can say varies with respect to. We can also say that it is a function of. Okay. Most of them, we will see this later. This varies with respect to. Respect to just is another way of saying depends on. So when we talk about like variables, we're putting variables in for these things, for time and for temperature. We're gonna most often use the variables x and y just for generic. Now we can use whatever variables we want. In math, it really doesn't matter. There are conventions for some things, but for the most part, you could just kind of pick whatever you want. But when we're talking about like just a generic function, we use x and y, where x is going to be your independent and y is going to be your dependent. And when you put it in a ordered pair, you always put the independent first because that is going to determine your dependent at the end. Okay, and note that if you're going to see it as, if you're going to write things as a sentence, you can say as the independent value increases or decreases, this is going to cause the dependent value to also either increase or decrease. So the key words here for these sentences, the words as, because, with respect to, they're going to tell you which one's independent and which one's the dependent. No matter which word or phrase you see here, the independent always follows after these words. So for example, in this note here, we say as the independent value. And if we look, further up here, we see with respect to, and time is your independent there as well. So, looking at an example, we're going to write a short statement that expresses a possible relationship between the variables of size of home and the cost to heat the home. So you need to know, okay, we have size and cost, which one depends on the other? So does the size of the home, is that going to determine the cost, or is the cost going to determine the size? Well, and we can look at the multiple choice here. If you're not sure exactly what it is, we can write out these sentences to see which one makes sense. So we have a bunch of different options here. So part A says, as the size of a home increases, the cost to heat the home increases. For B, as the cost to heat a home decreases, the size of the home decreases. As the cost to heat a home decreases, the size of the home increases. Or as the size of a home decreases, the cost to heat the home decreases. Like I said, as and because are the same. So if any of these, if none of these really make sense, or a lot of them do, maybe replace as with because and see if that makes more sense. So like for A, because the size of the home decreases, the cost to heat the home increases. Does that make sense? So if the size decreases, so a smaller house, does that mean the cost is going to increase? Well, no, that doesn't make sense, right? So because the cost to heat a home decreases, the size of the home decreases. So because it's cheaper, that makes the size smaller? Well, it's not because the cost is cheaper, right? So really the size is going to tell you what the cost is. So we want to have the size as part of our because. So size is going to be our independent here. So because the size decreases, that means the cost is also going to decrease. Okay, let's take another example. So again, write a short statement that expresses possible relationship. This time we're looking at the rate of pedaling and the speed of a bicycle. So which one is going to determine the other? Is the rate dependent on the speed, or is the speed dependent on the rate? So you can also think of like what comes first, right? So if you pedal faster, does that mean you go faster? Or because you go faster, does that mean you pedal harder? So like if you're going fast, that means you have to pedal harder. Or do you pedal harder in order to go faster? Well, of course, you're going to pedal faster to go faster on your bike. So we want the rate to be your independent and the speed is going to be your dependent. So we want it to say as the rate of pedaling. So we know that the rate of pedaling is going to determine your speed. So we know it's not B or C. So as the rate of pedaling, as the rate of pedaling. So as you increase your rate of pedaling, the speed decreases. Well, no, that shouldn't be the case, right? So it should be D, as the rate of pedaling increases. So as you pedal faster, the speed also goes up. Okay, so now representing functions. So there's three different ways, basic ways to represent a function. So we can represent it with a data table, or data table, however you want to pronounce that. um, that provides detailed information, but if you have a lot of data, it can get really unwieldy. So, for example, here we have this data table um, of different x's and y's. So, for example, you just have different values for x and y. So let's say if you put in a -2, let's say you get a 5. If you put a -1, you get a 7. If you put in a 0, you get a 9. Say you get a 1, you get 11, and 2, you get a 13. This would be a data table that represents a function. Okay, so you can also draw a picture or a graph that represents a function. So sometimes it's easier to draw a picture. Sometimes it's easier to graph the function. A picture could be like like blueprints. You have like the picture showing all the information, and those are great ways. It's a good way to consolidate information because you can put a lot of, like, for example, data points on one graph. So, for example, we could have this graph here. Let's say we have a line here, or we could have a curve. You know, just whatever your function is what could be displayed here. Okay, thirdly, we can write a function in the form of an equation, which is what we're going to be doing the most of. An equation or a formula. So that would be something like this: y equals 2x plus 1. And we'll talk about that in the next couple sections. Okay, another aspect of functions are domain and range. So the domain of a function is going to be all values that make sense for your independent variable. So anything that you can put in for your input and put in for x. And then range then is going to be everything you get for your dependent. So domain is independent and dependent is range. I kind of think of domain like your home base. This is where you start, and you always start with independent. And the range says how far can you go from your home. So based on those independent variables, where do those take you? And that would be your dependent. So for example, if we look at the time and temperature that we started with, our time is our domain, all the different times we're looking at, and all the temperatures of that day are the range. Now for time, we're not going to be looking at negative values, right? Because we're not looking at different times of day. We don't have negative time, right? Not really. That would be like before now. And then for range, we're not going to be looking outside the range of that particular day. So it looks like these range from like 50 to let's see, 73. So my range is going to be between 50 and 73. We're not going to look at like 30 degrees or 90 degrees because it didn't happen during those times. Now, because we're trying to deal with just numbers, we need to do something with this time instead of including all of these AMs and PMs. So here we have like a 6 a.m. and 6 p.m. So we're not just going to say 6, 7, 8, 9, 10, 12, or 9, 10, 11, 12, 1, because numerically that doesn't really make sense. So instead what we're going to do is we're going to change it so that it is a count, a quantity. So we're going to say we're going to start at 6 a.m. and we're going to count from there. So at 6 a.m. it's a 0 time because that is my start. We like to start at 0. And at 7 a.m. is 1 hour later, so I'm going to put a 1. 8 a.m. is 2 hours later, so I put a 2. And so on. That way we have this sequential numbering, and we have a way then to put it into a function. So we have this table. Now we can graph it where time, the domain is always on this x-axis, and the range is going to be on your y-axis. So to graph it, of course, at time 0, we're at 50. 1 hour later, we're at 52. 2 hours, we're at 55, and so on. So often when we do graphs, we're going to, put in all of our points, but then we're going to connect it with a line or a curve. So because this does seem like, for like the overall picture does seem like it's curving, and temperature doesn't just like jump, right? I'm going to connect these with a line, and that helps us make decisions on between the hours that we actually recorded. So if we were going to predict what the temperature was at 11:35 or 11:30, so 11:30 a.m. This is 5.5 hours after 6 a.m. So I'm going to look at 5.5 here on the graph. I'll do this in red so you can see a little better. So I'm looking at 5.5, and I'm going to follow that vertical line up until I hit the graph. And then to get the temperature, I follow it over to the y-axis and use that to estimate what the temperature will be. So if it continues this even curve here, at 11:30, I should be at about 67 degrees Fahrenheit. Of course, this is just a prediction. It may not be exact. We can also use it to say, okay, if I wanted to continue after 12 hours, it's going in a downward motion, so it might continue on. Again, these are all just models are there to help us make predictions and to make decisions. But of course, all of those decisions are only as good as the data and the assumptions that built the model. So if it's a good model with good data, you can trust your decision more. If it's a little bit iffy and you don't have a lot of data, then it's not as helpful. So here, if we had made more data points in between, it would be easier to predict. And if we'd only, check the time every 4 hours, that again would be less realistic or less helpful for predicting. Okay, let's look at an example. We have this graph here. So we're looking at different years and world population in billions. So each of these numbers here, they represent billions. So 1 billion, 2 billion, 3 billion, 4 billion, and so on. So part A, we're going to identify the independent and dependent variables, and I describe the domain and range. So independent variable, that's going to be your X value. So in that case, it is the year. The dependent variable is going to be the one on your vertical axis, which is world population. So those are the two things we're comparing. The domain of the function is going to be, again, your X values. So those are the years. For the minimum value, so we started at, the first data point is at 1950. And the last data point is here at 2000. Okay, so the range, that's going to be all of the Y values that are represented here. So this is going to be your population. The minimum value, that lowest point that we've got, is just over this 2. So I'm going to say it's about 2.25. Again, this is kind of an estimate. Well, it actually says round to the nearest integer. So round to the nearest integer is just going to be 2. So 2 billion. And the maximum right up here is just about on the 6 billion line. So between 1950 and 2000, the population was always between 2 billion and 6 billion people. Okay, now describing it in words. So if we're going to describe this function here and what happens on that graph. So A says the function shows an initial increase in population but then a decrease in population closer to 2,000. So that means that population is increasing, but then it decreases closer to 2,000. Well, it looks like between each of these, we're always going up. So there's not a decrease at all. So we know it's not A. For B, the function shows that the rate of increase in population has been increasing since 1950. So now it says the rate of increase has been increasing, which means that it is increasing faster. And we'll talk more about this in the next section, but if it's increasing faster, it should mean it, like in 1960, it would, in like the same amount of time, it would go further. So it looks like between 1950 and 70, it's about the same, but then it doesn't increase a lot. Then it increases more, but not a whole lot different than it increased here, about the same. So it doesn't look like it's been increasing the entire time. So we're going to say no. For C, the function shows there's been a relatively constant world population since 1950. If there's a constant population, that means it's not increasing or decreasing at all, and that's definitely not true. So it should be D. The function shows a steady increase in population from 1950 to 2000. So again, we see it's increasing at almost the same amount each time, except for this little bit between 1970 and 80. So it is option D. Example 4. So we have another graph. Identify the independent dependent variables and the domain and range. So here we have dates and we have high temperatures. So we have here on the X, we have the time, which is the day of the year. So again, like if we're measuring at different dates, we have January 1st, February 1st, February, March 1st, and so on. But, it's all kind of ones. So to make it better, we're going to do a count from the beginning of the day or beginning of the year. So January 1st will be the first day of the year. December 31st will be the ending day of the year. And because we're, this time doesn't just start and stop, we're not just going to be looking at certain days of the year, we're looking at the entire year. So the independent variable, of course, we have time and temperature. And of course, the temperature is going to be dependent on the time. So the date or the time of year is going to be our independent variable. And their dependent variable is going to be your average high temperature. For that day. Okay, so the domain we said was going to be, we're going to select either all days or certain days here. So like I said, because time works in a very fluid motion, we're going to be looking at all days and not just certain days of the year. So the range. So as we look at these temperatures, the range is going to be all the different temperatures that are possible within this calendar year. So we're looking at the ones that they've recorded. It looks like the lowest temperature they recorded was a 38. So it's going to be between 38 and the highest is, let's see, we have 85. Looks like that's the highest. So we're going to be looking at temperatures between 38 and 85 degrees Fahrenheit. Okay, so now let's graph this function. So the other one gave it to us this time. We're actually going to graph it. So at day 1, we're at 42 degrees, so that's just a little bit over 40 here. 32 is going to be my February 1st, because there's 31 days in January. So February is at 38, so that's just a little before 40. And March is at 48, so that's almost halfway between 40 and 60. So that's right at like 50 here. And then April is at 58, so that's almost 60. Again, this is just estimation. You're not going to be asked to do something like this on my math lab. They'll actually give you like a grid, and you can do it a lot easier than just on paper. Okay, so January, February, March, April, so we're on May, it's 69, so it's just under 70, which is halfway between 60 and 80. And then June is 76, so that is close to 80 here. And then 85, it's a little bit above 80. And 83 is about the same here. And then 80, 69, again between 60 and 80. 55 is almost at 60. 48 is right before 50, which is halfway between 40 and 60. And 44 is just above 40. Okay, so then we can connect these with a line. Okay, so that is the temperature graph for the year. Now if we're going to describe this graph, we have option A says the temperature decreases during the first half of the year and then increases during the second half of the year. Okay, so the first half of the year between 1 and 82. So it's saying it's decreasing in that first half. Well, it's increasing, right? So that's not that one. For part B, or option B, the temperature stays relatively constant throughout the year. So again, constant temperature would mean it would be like a flat line. It doesn't increase or decrease. And that is also not true. For C, there's no discernible pattern in the temperature throughout the year. Well, it does look like there's a pattern, right? It's not like up and down and up and down and up and down the entire time. It's not C, so it should be D. The temperature increases during the first half of the year and then decreases during the second half of the year. Well, that does look like it's true. So between January and June, it's increasing, and then after June to December, it's starting to decrease. So it is option D. Okay, and that is it for 9A.